get started. How's this volume? Can you hear me in the back? Too loud? Good? Great. Thank you. All right, so we're still doing deep learning. Last week, learned a lot about, the basics of neural networks, their structure, what they look like, how to train them. Sean came in on Friday and talked a lot about the practical tips and tricks. And this week, we're going to focus on a particular type of neural network, which has proven to be, quite important in the field of computer vision, which is called convolutional networks. Okay, so these types of networks are the most widely used class of neural network models for what we typically think of as like image-based problems, like trying to solve some machine learning problem from images as your input. Okay, and people broadly refer to this thing as computer vision, right? Computers and how we let them, be able to see the natural world. As it turns out, lots and lots of people care about computer vision. There's a lot of problems that you can specify from different types of images, like natural images, satellite images, medical images, all these different types of things. So computer vision, consequently, is also a very popular area for study. And because deep learning works so well, conv nets or convolutional networks then become a very popular class of models for solving all of these different types of problems. Conv nets can be used for other applications. So it's like what we're going to learn is not strictly, restricted to the image domain. And conversely, there are other types of neural networks that we can also use for computer vision. In fact, we'll talk a little bit about this next week when we talk about, a different type of neural network model. However, more often than not, conv nets and computer vision kind of go hand in hand. So this is kind of the easiest way to think about them. What we're learning about this week is a class of neural network models that not always, but is usually used for computer vision, and as it turns out to be a really good model for these types of applications. So today, and also next lecture, because we're going to need a little bit more time than just today, we're going to cover some of the motivation behind convolutional networks, detail what they actually look like mathematically, and then also, sort of draw the same types of, diagrams that we were drawing last week, for how to understand these types of networks. And then we're going to cherry pick a little bit and talk a little bit about, over the last 10 years or so, what people have been studying with regards to conv nets. But first, there's actually something else that I want to show you. And maybe, I can relate it back a little bit to how we can motivate conv nets and why we're studying them. But really, I want to show you this just because I think it's kind of cool. Okay, so I think Sean O last Friday told you very briefly about this new AI system that came out called DALL-E 2. It's this really impressive system, actually, that basically generates images given language, given text that you provided, right? And the images that it generates are, oftentimes photorealistic, or you can ask for really good paintings or digital art or all this other type of stuff. Well, they gave me early access to it, so I was playing around with it, and, the thing that I really wanted to do was I really wanted DALL-E to generate a picture of my dog, right? Because I think that that's kind of the funniest thing that we can do. So I gave it this sentence: a painting of a small brown terrier, that's my dog, with round ears, and I wanted it to generate, a painting of my dog that was regal, right? So it would be, look, very kingly. So this is my dog, Peanut. This is not the image that DALL-E generated, but I really wanted something that would imagine my dog as some kind of king, right? And then once you feed in the sentence, well, the system will generate you a whole bunch of different, things based on what you asked for. And one of them actually turned out to look quite a bit like my dog, Peanut. So this is one of the paintings that DALL-E generated me, and I thought that this was really quite impressive. And my plan is to sort of print this out and frame it up and hang it up on my wall, because I think it's quite nice. However, you will notice that there is, in my opinion, a small flaw with what it generated, which is that my dog Peanut's ears are not quite that pointy. Okay, so I asked for round ears, but it kind of gave me pointy ears. Well, actually, this system is quite impressive. One thing that it'll let me do is erase parts of the thing that it generated, and then ask it to regenerate those parts. And because it's got some amount of randomness to it, it'll regenerate new things whenever you ask. And so that's exactly what I did. And then it gave me a painting where the dog has rounder ears, and that looks quite a bit more like Peanut. So I thought this was, kind of cool. And really, the only reason that I'm showing you this is because I think it's hilarious. But, underneath the hood, part of what's going on is the power of convnets. Okay, so if I were going to try to explain to you how this whole system works, it would take a while, right? There are a lot of moving pieces. It's quite complex. But I was thinking about it, and what I realized is the first thing that I would probably try to explain to you is what a convnet is and how it works. And then from there, we can sort of move on and learn all the other pieces. So this really is a fundamental building block of what a lot of people are doing, and you can build a lot of really cool things with these ideas. So just to know that, what we're learning is, somewhat relevant, at least to, some of the things that people are doing and the types of systems that people are building these days. I'll just leave that up for another 5 seconds. All right, great. So let's actually get started. So we're thinking about computer vision. We're thinking about processing images, right? So we have this picture that we've drawn previously about what a neural network looks like, where we have, our input X fed through all of these nonlinear layers. And then if we're doing something like classification, eventually we'll get to the point where we take that final output and we pass it through a softmax, right, in order to try to get our predicted probabilities. That's kind of the big thing that we're doing, right? And we're trying to learn all these nonlinear layers so that we get some feature representation upon which a linear model will then do well. That's the high-level motivation, right? Well, now, let's imagine that this X that we're passing in is an image, okay? So images are quite complex. Images are typically represented as a large collection of pixels, right? Spatially organized pixels. And there are oftentimes many, many pixels in an image. So we can imagine a pretty modestly sized image, actually. Like we can imagine that something is 224 pixels by 224 pixels. This is not a large image, but it captures some amount of resolution, and we can sort of, imagine that the image could tell us something about like an object or something like this. And then oftentimes we're working with color images, right? So actually every pixel, so to speak, is actually 3 different values of red, green, and blue, right? So if we have this 224 by 224 color image, how many pixels do we have? As it turns out, we have over 150,000 pixels, right? So in the native representation, the sort of explicit representation that I'm giving for this image, we can almost think of it as a vector of 150,000 dimensions, okay? It's actually spatially organized, so it's not just a flat vector, but we can sort of think of it as a flat vector if we wanted to, right? This is quite a bit larger than really the types of features that we've thought about so far, right? So 150,000 dimensional vectors are not particularly easy to deal with, and especially not when we start thinking about these neural networks as we've learned about last time. Okay, so what did a neural network look like last time? Well, we had this linear layer, right, that goes from whatever input dimensionality we have to the next hidden dimensionality, as we call it, right? And then we pass that through a nonlinearity, and then we have another layer that's like another matrix multiplication, so on and so forth, right? So if we imagine that, let's say that, we make our hidden dimensionality, which I'll call, ZL, the dimensionality of ZL, relatively small, like something like 128 dimensions, okay? This is probably in reality a little bit too small. I can't just go from 150,000 dimensions down to 128, but we're thinking in terms of, just even if we did that, how many parameters would I need in this first layer? Well, roughly speaking, how many parameters I would need would be the number of weights that I need to define in that matrix, right? That goes from input dimensionality to output dimensionality, right? And that in this case would be over 150,000 times 128, which is something along the order of 20 million parameters just in my first layer alone, okay? So when dealing with images, this type of neural network, the simple neural network architecture that we talked about last time, it doesn't scale well at all, okay? So these images are very, very high dimensional, okay? They have tons and tons of pixels, and we're sort of ignoring everything that we know about images, like all this spatial locality and all this other type of stuff, when we're designing what we call fully connected networks, right? This is called fully connected because there's a connection from every output dimension to from every input to every output dimension, right? So in these fully connected networks, when we have really high dimensional inputs like images, it turns out to be a pretty bad idea because we're going to get a huge number of parameters in our model that we have to learn, and typically doing so requires very, very large data sets and doesn't really scale well to the types of problems that we're trying to solve. So this is kind of the big idea behind what's the issue behind taking the neural networks that we learned about last time and trying to apply them directly, naively, to these types of image problems. So then we might ask, what can we do instead? Well, someone came up with a different type of neural network, which is a little bit more efficient, a little less general, but turns out to work really well for images in particular. So the key idea behind this class of networks called convnets, convolutional networks, is that we can reduce the massive number of parameters that we need because we know something about the spatial structure of images. Okay, in particular, what we know is that many, many useful image features are what we call local, which means that they're only, they can be extracted just by looking at small patches of the image rather than having to understand the entire image as a whole. Okay, so this is the basic idea. Many useful image features that we might want to learn are local, and can we do that can we use that to somehow reduce the number of parameters that we need? What do I mean by local features? People used to hand design local features for these types of image-based problems. This is kind of what I told you about last Monday, right? For example, hand-designed features for images oftentimes extracted things like edge information. Well, edges are local features in the image, right? We take local patches, and then we look at all the different edges in that local patch, and then what this does in particular is construct histograms out of that and stuff, but the high-level idea is that we're looking at local information in the image in order to try to get useful features for how to understand that image, right? And so we're going to be taking that same intuition today about local information, but we're not going to be actually designing features around this. We're going to be trying to use that to build our neural network such that our neural network understands how to extract that information by learning it. Okay, so that's kind of the big picture. So we're not going to go quite as far as hand designing the features like we used to do, right, pre-deep learning. But what we are going to do is we're going to place limits on the types of features that can be learned via the architecture of the neural network, how we actually build the neural network, okay, how we specify what the layers are and what operations they perform. That's what we mean by architecture, right? So we're going to somehow specify this architecture to be one that pays attention to only local information in the image, and then doing so is going to allow us to reduce the number of parameters that we need, such that we're no longer working with these, massive, fully connected networks that just have way too many parameters for efficient learning. This is an idea known as inductive biases. Maybe you heard this term last Friday, maybe you don't exactly know what it is yet, but it's actually quite a simple idea. An inductive bias is basically knowledge that we build into our model in order to make it learn more effectively. So we as humans know something. Can we somehow translate that into either the model architecture or its training procedure or something along those lines in order to make it learn more effectively beyond what it can just pick up from the data? Okay, so inductive bias versus learning can oftentimes be thought of as nature versus nurture. Okay, so learning is kind of the nurture, it's what you gather from the data, and then inductive bias is kind of like the nature, is how you were built or how you were specified in order to learn more effectively. So this inductive bias here is that we're going to build our neural network such that it's biased towards only learning local information in our image rather than something that pays attention to all the different dimensions all at once. It's often the case that inductive biases are needed in order for most effective learning. We as humans sort of know a lot about the different domains that we're working on. And we want to be general in the sense of learning all these features and doing all this stuff, but usually there's a trade-off in terms of we will also want inductive biases when they're appropriate, such that we can maximize the efficiency of what we can extract from the data. You might also be wondering, well, it's nice that we can capture local information. Of course, there's very important local information in images, but surely there must be some useful non-local information as well, right? And am I losing that if I define a type of neural network architecture that specifically by design does not pay attention to that? The answer is we'll get to that in a bit, and we actually, discuss what our full neural network architecture is going to look like. Okay, so what does a locally connected layer for processing images actually look like? Let's say I have this image. Okay, I can also represent this image, and it's going to be a little bit easier diagrammatically to do so. I can represent this image as this other sort of, what we usually call a tensor, right? So something that's higher than 2 dimensions, we'll call a tensor. 2-dimensional things we call matrices, 1-dimensional things we call vectors, right? This thing we're going to call a tensor. It's got 3 dimensions, and when we're talking about images, we usually call these 3 dimensions height, width, and depth. Okay, so height and width are like how many pixels long and wide this image is, and then depth is usually like 3 or 1, depending on if we're working with color or grayscale images. Okay, so we have this image is 224 by 224 by 3, and then what we're going to say is, well, let's actually just process local patches of this image. Let's imagine that I'm going to take a look at all of the different 3 by 3 pixel patches of this image in order to try to extract features from every single 3 by 3 patch. Okay, how would I do that? I can define my weights, my parameters, as some 3 by 3 by 3 tensor. Okay, so this tensor has height, width, and depth, all 3. And what I can imagine doing is I can take that tensor and then do a multiplication with any particular 3 by 3 patch of my image. That'll give an element-wise multiplication, right? What that'll do is that'll give me, 3 by 3 by 3 numbers, and then I can sum all of those together. So a typical like dot product, just a higher dimensional dot product is kind of the way to think about it, right? And if I do that, then I can get a single number out of that transformation. Okay, so I have a weight tensor, is what we can call it now, right? Because it's 3-dimensional, and it's 3 by 3 by 3. And I can look at a 3 by 3 by 3 patch of my image, multiply all of this together, and then sum all the numbers in order to get a single output, which is like a matrix multiplication of sorts, out of this operation. If it's easier for you to think about, you can also just imagine just flattening the whole 3 by 3 by 3 thing, right? And then at that point, it just looks like a normal dot product. We just sort of have it arranged spatially because we understand something about the spatial structure of images. So I could get a single number out of this for all the 3 by 3 by 3 patches of my image. But on top of this, I can also define additional tensors that might contain other settings of the weights that give me different numbers, right? So I can do this as many times as I want, right? So I could have another 3 by 3 by 3 tensor that has different weights, as we call it, different parameters in it. I can also, apply that to patches of my image and get a different number out, so on and so forth, however many of these I want, right? So this whole collection of, these tensors is usually called a filter. Okay, this is a filter that for every patch of my image will give me some number of outputs, and the number of outputs is dependent on how many tensors are in my filter. And oftentimes we can actually visualize these filters, and it turns out that they actually look like they're extracting some interesting information like color information, edge information, and all of these different types of things. But the important pieces to know are this filter is kind of what defines my parameters that I actually learn. Okay, so it's some number of tensors, depending on how many outputs that I want, that are operating on some small patch like 3 by 3, for example, on my image. There was a question? Are these tensor weights necessarily on top of each other? Yeah, right. So good question. So the reason that I drew all of these tensors on top of each other is because we're imagining the situation where they're all operating on the same patch of the image. Usually that's how these are used, where the tensor all looks at the same 3 by 3 patch and then outputs some output vector depending on how many tensors you have. All of that was correct, yes. So before, we had about 20 million parameters in our layer that was going from, image to some hidden dimensionality. We can ask, how many parameters do we have now? Well, this filter, as I've drawn it here, it has 4 tensors. Each of these tensors has 3 times 3 times 3, which is 27 parameters. So now we have 108 parameters in total. If we add a bias term to this output, so we add a 4-dimensional bias to change all of the output numbers that we now have 112 parameters. So it's not exactly the same thing, but we can see clearly what's going on here is that we have a much smaller number of parameters for transforming the image into some hidden representation compared to when we had the fully connected network from before. But wait, we have not yet processed the whole image, right? So what I've told you about right now is actually just processing the first 3x3 patch of this image. We need to do a little bit more work in order to actually process the rest of the image, right? Well, as it turns out, the way that convolutions usually, described is that we're not actually going to need any additional parameters for processing the rest of the image. We're just going to take the same filter and run it across our whole image. But we'll describe that in the next slide. I think there's a question. Yes. Oh, sorry. Yes. Let me distill down the question. There's a question about this bias term, which is like something that you add to the output, versus the term that I used on the previous slide, inductive bias, where the term bias there is actually being used completely separately from this bias that we have here. Why it's called an inductive bias is because we're basically biasing our model towards certain solutions. And then making those solutions more likely and making other solutions less likely. Here, bias literally means like bias in terms of like, a linear transformation that is actually an affine transformation. So I know it's confusing because the same term is being used, but they're being used in 2 completely different ways. So no relationship is the short answer. Okay, so some of you might know what a convolution is in terms of, the mathematical operation. That will help you a little bit in terms of, understanding the intuition behind convolutional networks, although you should know that the term convolution is used quite loosely in convolutional networks. So, if the math doesn't look quite like a convolution to you, that's okay. And if you don't know what convolutions are, maybe that's okay too, because, it doesn't really mathematically line up anyway. So, here's our image. And what we've said previously is that, we're going to apply this filter onto the first 3x3 patch in our image. And that's going to give us, these 4 outputs, right? You'll see I've drawn a little red grid on the image to denote sort of the patch that we're looking at. Okay, obviously not drawn to scale. That red grid is much larger than 3x3 pixels, but you get the idea. What we're going to do in order to process our whole image, rather than defining more parameters, let's actually take that same filter and just slide it across all the different 3x3 positions in our image. So we like move the filter 1 over, right? And then that will process the next 3x3 patch in our image and get us another 4 numbers out in our output. Maybe it's not the same 4 numbers, right? Because the image patch has changed, right? So those colors don't necessarily mean that we're getting the same numbers. It's just, denoting the different tensors in our filter. And then we rinse and repeat this process onto, the next 3x3 patch of our image, so on and so forth, all the way across our image, and then we start moving down, into like the rest of the dimensions of our image as well, in order to get all of the different outputs that we want. So we process this whole image using the same filter. So in the end, we will still only have 112 parameters like we had before. So no increase in parameters, just a particular operation for how we're actually using this filter to get the output that we want. What does our output look like? What are the dimensions of this output that I'm producing after I slide my whole filter across my whole image? Yes. It's another tensor. How many dimensions does this tensor have? Perfect. The output, right, from this operation, this convolution operation, as I call it, is another tensor. It's got some height, it's got some width. Maybe it's like close to 224, maybe it's not exactly 224, but it's pretty close, right? And it's got depth 4, because I specified that this example filter that I'm working with has 4 tensors in it. So the output actually quite similarly looks like an image itself. It's not exactly an image, right? It doesn't have like 1 or 3 depth necessarily, but it kind of looks like one. It's got a height and a width and a number of channels, right? And this is perhaps quite interesting. Why is it quite interesting? Well, maybe you already have an idea why this might be quite interesting based on the basic idea of deep learning as, you know, composing transformations together, but we will get to that at the end of the next slide. First, let me tell you a little bit about what the dimensions and the shapes of this actually look like when we write them all out mathematically. So the processing step that we have just described is referred to as convolution. Not exactly mathematical convolution, although pretty close. It's just what people call in deep learning because it sounds better than like cross-correlation or something like that. Convolution is performed with a filter. So the filter we can think of as an even larger tensor. So I was using the word tensor before to describe these 3-dimensional things, right? But tensor can really mean like anything that's higher dimensional, right? So we can also call the filter a tensor that's 4-dimensional, right? It's 4-dimensional because it's got a height, width, and a number of channels. That's k, and I here, right? So usually we assume that the height and the width of the filter are the same. And then it's also got this other dimension O, which was 4 in the previous example, right? It's the number of outputs that we're actually producing, right? So we can think of this filter as a 4-dimensional tensor, and then also we have this O-dimensional bias term that we're adding as well, right? So then this gives us basically the set of weights that we're trying to learn inside a convolution operation. In particular, what I'm describing to you here is something called a 2D convolution. Okay, why? Because it's got 2 dimensions, height and width, right? I could also think about 1D convolutions, maybe if I had a 1-dimensional sequence, right? Like an audio waveform or something like this. And 1D convolutions are sort of a separate topic, but in vision, since we're dealing with images usually, we're talking about 2D convolutions. I can expand this into more dimensions if, for example, I'm working on like video. Maybe I want to work with 3D convolutions because I also have a time axis, right? But we're going to talk mostly about 2D convolutions, and this is what a 2D convolution looks like. It's got this 4-dimensional filter tensor that we're working with. So 2D convolutions take in an input of, you know, that's a tensor with size I, H, and W. I is the number of input channels. For an image, that's usually 1 or 3, right? Grayscale or color. And then also some height of the image in pixels and then some width of the image in pixels. Or we can swap these around, transpose these, and get HWI depending on the convention that we're working with. That's not super important. Just wanted you to know that different people do it in different ways. And then it's going to output a tensor of size number of output channels. Again, that was 4 in our previous example, right? And then some other height and width, H prime and W prime. Okay, maybe these H prime and W prime are pretty close to H and W, but they don't necessarily exactly have to be the same. What are they in particular? It depends on certain values of hyperparameters that we have yet to specify. So we're going to specify that 2 slides from now. So because the output has similar dimensions, right? We put in something that was IHW. We're getting something out that's OH prime W prime. We can imagine stacking convolutions on top of each other, right? So I take my input and I process it using a convolution operation. That gets me another 3-dimensional tensor. It's almost image-like, right? I can put another convolution operation on top of that and then get another output, another convolution, another output, so on and so forth, right? Just in the exact same way that we imagined stacking all of these nonlinear layers on top of each other last week, right? Is that how we're going to make deep convolutional networks? That is part of the story. And that's basically the idea, the central idea behind these conv nets is stacking convolutions on top of each other in order to do finer grained processing of these images that pays attention mostly to the local information in the image. Remember, there was one point that we brought up before, which is we don't just necessarily want to pay attention to local information, right? Maybe there is actually some non-local information like objects that are far away in the image or something like that that we do want to pay attention to. How do we actually do that? We do that by actually stacking convolutions. That's the big idea. And the reason this is useful is because what's basically happening is that stacking convolutions increases what we call the receptive field the deeper we go, the more convolution operations we stack on top of each other. When I say receptive field, basically what I mean is a particular output, what can it depend on as a function of the input, right? So an output after one convolution operation can only depend on this 3x3 patch. But what about in the next layer? Does the patch expand? How much of the input image can I actually look at when determining this particular output at a particular layer? Here's a picture of what that looks like. So I have this, here I'm only drawing 3 tensors in my filter now just to make things more compact. If I produce an output, right, which in this case would have, 3 by height by width, right, because I'm using 3 tensors in my filter. If I produce this output, right, and then I think about what can this first, or actually, I guess I drew the second layer. Okay, so if I take this image and then I pass it through this convolution operation, get another thing that kind of looks like an image, pass that through another convolution operation, right? And then I look at that output from like this particular operation, okay? And then I think about, well, these outputs here, these dots that I've drawn, what can they depend on as a function of the original image? Well, these dots, right, were produced as a function of the first 3x3 patch in my hidden outputs, right? Not the original image, but the thing that I got after the original image. And if I think about that 3x3 patch in my convolution output, in my first convolution output, right? Well, that actually depends on a 5x5 patch in my original image, right? Because the first thing in that 3x3 patch depends on the first 3x3 thing in the image, but then the last thing in that 3x3 patch would depend on this 3x3 patch sort of shifted down in the original image. So then that in total gives me a 5x5 patch in the image that I can be looking at when producing this output of my second convolution operation. So that ends up looking like this, right? I have this whole 5x5 patch in the original image. That grid is now larger, right? The whole 5x5 patch in the image that I can be looking at. This story only expands as we keep putting these convolutions together to the point where, at some point if I have many of these convolutions stacked on top of each other, maybe I can be looking at a very large piece of my original image, maybe the whole thing if I go deep enough, right? So at some point, stacking these convolution layers on top of each other is going to let me extract more useful non-local information as well, because this receptive field keeps growing the deeper we go. That's kind of the high-level idea. And this picture that I've drawn, we can also succinctly draw it in a similar way that we drew neural networks before, right? Where I can say X is transformed by a convolution into some hidden representation Z1. I can transform that again into a using a convolution because it's also image-like in its dimensions, right? Into Z2, and so on and so forth. And if I'm doing like something like image classification, then at the end, I might pass that whole thing through a softmax in order to get my predicted probabilities. Yes. Do people combine convolutions with like fully connected networks? Yeah, we will talk about that, but the answer is not usually like in an interleaved fashion, because that doesn't quite make a lot of sense, but we can do like one after the other. Sometimes people do that, and we'll talk about that. Yes. Is there any nonlinear functions? You're cutting ahead of me, but yes, we will talk about that. Spoiling my punchline. Okay, so how do we actually determine the height and the width of the output of the convolution layer? I told you it depends on certain hyperparameters, and we're going to talk about those hyperparameters here. There's two important hyperparameters that determine the size of my convolution output. Okay, what are h prime and w prime actually? Well, it depends on a couple of things. So first, there's a hyperparameter called padding, which is basically what it sounds like. We can choose whether or not we want to pad our input by a certain number of quote-unquote pixels on all sides. Okay, so imagine I had like a 224 by 224 image. I can imagine padding both sides, or all four sides, right, with like 2 pixels, and then I have a 228 by 228 image at that point, right? So I can do this padding because basically this convolution operation kind of cuts off the sides, so to speak, of my image, right? Because I slide my filter along the image, but it stops at the ends, right? So however large my filter is, it's actually going to cause the output to be slightly smaller than what the input was, right? Because I don't have the same number of outputs when I'm sliding my filter across compared to the number of inputs I actually have. Padding can help fix this, right? The most common choice is to pad with zeros, because it's just so simple, right? There are more complex schemes that people have come up with, but when combined with normalization, with input standardization, and things like you learned on Friday, right, about like batch normalization, layer normalization, things like this. When combined with normalization, padding with zeros is usually perfectly sufficient for getting good performance, because things look like mean zero anyway. So having a zero value at the end doesn't seem all that weird. The other hyperparameter is something called stride, which is basically every time I shift my filter over to process a new patch of my image, how much do I shift it by? Okay, am I shifting it only 1 pixel at a time, right? So I'm getting these overlapping patches that I'm looking at in my image, or maybe I'm shifting it by the number, or maybe I'm shifting it by the size of the filter so that I only look at non-overlapping patches in my image, right? So this stride is also important. It determines, am I looking at overlapping versus non-overlapping patches? How efficient is my operation going to be, right? Because the larger the stride, right, the fewer of these, filter operations I actually have to do. So this is also another important hyperparameter that also determines how large the output is going to be, right? But typically, the most common number is 1 per stride. You're just, moving over 1 pixel at a time. There is a formula based on pad and stride for how large your output is going to be. If you have a k by k filter, h prime and w prime is governed by this particular equation over here. It's the size of your input, hw, right, plus 2 times your pad, because you're padding usually both sides by the same amount, minus your actual filter size, like how large that filter actually is. And then you divide it by the stride, because that's how much you're moving over by every single time, and then you add 1 to the result of that. Do you have to memorize this? No. But if you ever need to actually compute what h prime and w prime are, this is the equation for doing it. It is quite common, like we said before, to choose a stride of 1, and then in total, right, so divide this number by 2, pad by the size of the filter minus 1. So for example, 1 pad on all sides for a 3 by 3 filter, such that you get the same dimensionality in your output as you did your input. Okay, this is the most common choice. It makes things a whole lot simpler, because I don't have to think about how my output is shrinking all the time or anything like that. I just keep things consistent all the way through. Question? Right. So padding refers to how we're padding the input, not how we're padding the filter. We don't usually do anything in terms of padding the filter. Wouldn't really mean anything, yeah. All right, so someone kind of stole my thunder earlier, but let's imagine convolutional networks attempt number 1. So the idea that we already have, right, is that this convolution operation is pretty convenient, because it takes in something that looks like an image, and then it outputs something that looks like an image. So then I could just keep stacking these on top of each other and keep doing continual processing of my image, right, in order to try to get a representation that I'm more happy with, that's easier to work with, that's extracting all of this local information, but as I go deeper, I can also maybe pay a little bit of attention to non-local information as well. So can we just stack convolutions on top of each other? Could I just do X convolution operation as we've described it goes to Z1, another convolution goes to Z2, yada, 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 as many of those as we want until we get to something that we're happy with, we put a softmax on top of that, and then those are our predicted probabilities. Can we do this? The answer is no, but why? Why can't we do this? What is the issue with this? Yes. Yes. So the output of the convolution for one particular patch and one particular tensor in the filter is a number, but remember when we're sliding the whole thing across, we are getting something that looks like an image, okay? So the issue is slightly different. Somebody already said it earlier. Yes? Yeah, so that's actually the same problem that we talked about last time, which is that convolution is a linear operator. Okay, it's a fairly complex looking linear operator. It's not just a matrix multiply. What actually is just a matrix multiply, right? But with a special matrix that you have to define. But nevertheless, it's linear, right? And what happens when we have linear operators stacked on top of each other? It's just a linear operation in the end, right? So even if I stack a million convolutions on top of each other, there's still a way to describe that as just some matrix multiplication with a fairly complex matrix, right? But it's not really getting me any more expressive power, right, in terms of getting complex nonlinear features of my input that are hopefully easier to work with than the original image itself. That's the whole goal behind deep learning in general. We're not quite accomplishing that when we just stack convolutions on top of each other. So what do we have to do? We have to introduce nonlinearities, right? Just like we did last time, we're going to introduce nonlinearities and then imagine this situation where we're sort of interleaving these different operations together, right? Linear convolution operations with nonlinearities that usually, like we said before, just operate element-wise, right? In order to, produce something that at the end is not going to be just a linear function of the input. So we will interleave our convolution linear operation with a nonlinearity, something like a ReLU, right, which is from a rectified linear unit. It just cuts off all the negative inputs. Applied element-wise to the output of the convolution. So this whole time, or hopefully this whole time, I mean, I'm not paying too close attention, but this whole time, hopefully, I've been referring to this, input convolution output as a convolution operation. Okay, that term is used purposefully because oftentimes the term convolution layer is reserved for something else. It's reserved for this fairly popular recipe for building convnets, which is convolution operation, followed by a batch normalization, which you saw last time on Friday, followed by a rectified linear unit. Other people refer to convolution as just the convolution operation, or convolution layer as just the convolution operation. But let's try to be consistent, so we'll just pick one, right? So if I'm just talking about the convolution, I'll call that an operation. If I say layer, that means that plus batch norm plus ReLU. Or some, suitable, mix in there where maybe I could replace batch norm with layer norm if I wanted to. I could swap out the nonlinearity for something else. But this general idea of convolution, normalization, nonlinearity is what we're going to refer to as a convolution layer. So it's like the analogous thing to like the nonlinear layer that we talked about previously. So you saw batch norm and layer norm last time, right? Like you normalize across your mini batch of inputs for batch normalization or across your feature dimensions per input for layer normalization, right? We can do similar things here, but actually the story here is actually going to be even simpler than batch norm and layer norm for arbitrary vectors. For images, we use these techniques in a very particular way. So batch norm is going to be operating on inputs of shape what we call N, C, H, and W, right? C, H, and W are the dimensions that we had before. Number of channels, height, and width, right, of the output of a convolution. We have an additional N, which specifies the number of images that we have in our mini batch, right? Here, when we do batch normalization, we usually compute statistics across N, H, and W rather than just N. Okay, so we're actually only going to get C, which is usually 3 for images, right, which is why I held up 3 fingers just now, but whatever C is, right, we're going to get that number of normalization statistics, that number of means and standard deviations that we're standardizing by. And then for layer norm, we usually compute statistics across C, H, and W, right, rather than just something like C, right, in order to get, the statistics that we're going to normalize by. All right. There's another fairly common operation that people use in convolutional networks. It's getting less and less important all the time, but still, it's an important thing to know about. It's called pooling. And pooling basically is what it sounds like. Pooling layers pool inputs together into something that's lower dimensional. Okay, reduces the size of the input, and consequently, when the size of your input is reduced, oftentimes that'll also mean that you need fewer parameters later on in your network, right? Because you're working on smaller inputs. It doesn't directly reduce the number of parameters, but it can help alleviate the need for a large number of parameters. Pooling uses something called a window size. Oftentimes 2 by 2 is quite popular, and a stride, right? So a stride here means the same thing. How much are we moving over every time we do pooling? And typically here for pooling, the stride is whatever the window size is. So if it's 2 by 2, we're going to stride over by 2 every single time so that we're looking at non-overlapping parts of our input. And it slides over the input specified by these hyperparameters. Oftentimes what we're doing is we're going to pool the output of a convolution layer in order to make it something smaller. What does that operation actually look like? Well, there are a couple of different versions of this. A quite popular one is something called max pooling, which basically only lets through the largest element. This is a nonlinear operation, right? Because we have to compute the max over this 2 by 2 window and then only allow through whatever was the largest one that we had. There's also average pooling, which is basically look at this 2 by 2 window of this part of my input and then average all of those values together, and then that's the output that I'm producing. So both of these we can see as just operations that are reducing the size of that input into something that's smaller that might be easier to work with subsequently in the network. In particular, if my pooling uses a 2 by 2 window size and a stride of 2, then the output is only 1/4 the size of the input, right? So this is a pretty effective way at making things smaller as I move through the network. So now we're going to finish with convolutional networks attempt number 2, which is going to be our successful attempt, okay? A simple, but still powerful convolutional network repeats this recipe of convolution followed by usually batch norm, but just some kind of normalization, followed by usually ReLU, but just some kind of nonlinearity, right? Repeats this L times. That's the number of layers that we have, right? In order to process our input image into some representation AL that's a nonlinear function of the input and hopefully is more suitable for the particular task that we're trying to solve, right? Rather than working with the input directly, right? Oftentimes we might throw some pooling layers in the middle there in order to reduce the input dimensionality as we go, but that's a design choice. And then oftentimes what we'll do is we're going to take AL, which is still like an image, right? It's still like 3-dimensional, right? And we just flatten it into one single flat vector, or we might do some kind of average pooling in order to turn it into a flat vector. And then after we get that one-dimensional vector, we can then pass that through one or more linear layers or fully connected layers. This is the question before about, like, can we combine convolutions and linear and fully connected operations? Yes, we can. Usually it's convolution followed by fully connected layers. And then finally get, the predicted probabilities that we want as a softmax on top of our final layer. So this is what a simple convolutional network looks like, and this is kind of the basic recipe that people follow when trying to, build a convnet for their application. Oftentimes there are going to be design choices that are involved with this, and people have come up with, a number of convnets that generally work quite well, and they all, for the most part, just kind of follow this general recipe in order to, build models that work. Okay, so that's all we had for today. There's the final diagram, and yeah, we'll leave it here. Thank you.